Hey students, I'm at the laundromat. I hope you can hear me. We are doing our laundry here. We don't have our washer and dryer hooked up at the new house. They're just sitting there. And I'm gonna do this review for you. It's essentially the chapter 6 packet that we've gone over in class, but this would be a good review. And it also will have the parts that we didn't get to in it. Hope you enjoy. Okay, the first question asks, reflection symmetric figure, what is it? And our answer was, when you reflect a figure over a reflecting line, it's the same and coincides with the pre-image. We used the illustration of a leaf hanging out in the wind. We'll use a very simple leaf. And it's caught on a spider web. And if it were to spin 180 degrees when you weren't looking, you might not notice that it turned 180 degrees. So it coincides with itself. So that is what a reflection symmetric figure is. The spider web itself that goes through the leaf, we might call the symmetry line. Y'all used some examples. You said the very middle, the line you reflect over, or a figure. So, man, I've followed the notes. The line you reflect over for a figure to remain the same. That is pretty good. Okay, next thing, the flip-flop theorem. If f and g are points and figures, then if I reflect over some line m, this would be our symmetry line, figure f, then I would get g. And if I do the same thing, if I reflect g over line m, then I get f. So I can flip one way, flop the other way. Both these things have to be true for the flip-flop theorem to apply. It can't be like one or the other, because this would be true in any old situation, not just in situations where reflection symmetry is present. Okay, that kind of answers how does it relate to reflection symmetric figures. So we basically said that. We said the reflection over some line yields the same image. This is reflection symmetry. Okay, segment symmetry theorem. Where are the symmetry lines of a given segment? We said, I have a segment here. That's this dark line. I can label it. We'll say L and M for laundry mat, or Fiesta Laundry is where we are in Candler. And I said I have a line. The line that contains the segment itself, line LM, is the symmetry line for the segment. So this is like a stick, or imagine this pencil just rotating. If this pencil was infinitely thin and didn't have the little nub on the end, that would be a symmetry line. Or I could pick the perpendicular bisector of my segment. That would be this line here. That would also be a symmetry line for the segment. Boom. The side switching theorem. This is basically saying if I have any given angle, what is the symmetry line for that? And it is the angle bisector. And so you can imagine my angle, if I was walking in the forest for mathematics, and this was my little spider's web. If I had a little spider's web right here, and the angle is just hanging there, I could spin this angle and it would coincide, it would live in the same place. I realized I had some grease on my fingernails from working on my bike. I'm not as dignified as maybe I should be. Circle symmetry theorem. A circle is reflection symmetric where? Reflection symmetric where? Well, how many lines of symmetry does a circle have? Infinitely many lines. So any line that passes through the middle, the center point of my circle, is a line of symmetry. So there's infinitely many. And the symmetric figure theorem is fairly comprehensive. We drew this little shape and we said any pair of corresponding parts in the symmetry are congruent. So I've got this shape, it's floating in the wind, and I can flip it over and it can coincide with itself. So any part corresponding to any other within the symmetry or over the reflection is congruent. This is a direct result of the A, B, C, D theorem. The ABCD theorem, which says that reflections preserve angle measure, betweenness, collinearity, distance, and we could really say a one-to-one correspondence. That's 6-1. 6-2. Name the parts of an isosceles triangle. Okay, we've already got it labeled here. We have a vertex, that is like the top of it. We've got sides or legs. Remember, isosceles in Greek means two-legged, and it's two equal-legged, or it might mean equal-legged. Iso, I think, means something like equal. I should ask Mr. Dutinsky about that, but heard this on Jeopardy many years ago. The angles that are adjacent to the base are called base angles, which will come up again here in a minute, and our base is, of course, called the base. Those are the parts of an isosceles triangle. The isosceles triangle symmetry theorem. Where is the symmetry line for an isosceles triangle? Well, we can describe it in three ways. This also relates to the isosceles triangle coincidence theorem. The isosceles triangle symmetry theorem just says I do have a line of symmetry in a isosceles triangle. I'm going to try and keep my camera steady. This is my vertex, and these two sides are the same length. From the midpoint of the base, this is my symmetry line. So remember, I can flip this figure over in the wind, 180 degrees, and if I imagine it just floating there, and it lives in the same place. This leads us to the isosceles triangle coincidence theorem. So there's a coincidence that these three lines, the median, which I can describe as the line from the vertex to the midpoint of the opposite side, in this case the base, that's one line. Another line is the perpendicular bisector of the base. Oh, lo and behold, that's the same thing. And our third line is the perpendicular bisector of the vertex angle, which lo and behold is the same line. What a coincidence. Why do they call it that? Oh, it's the isosceles triangle coincidence theorem. Well, it's probably a little backwards. It is a coincidence, and then they named the theorem after. Okay, ITBAT. What does that stand for? Isosceles triangle base angle theorem. This says the two base angles are the same in an isosceles triangle. We'll hit a theorem in a while that in pre-calc, this is intimately related to what we call the law of sines. However, we're not there yet. So we learn ITBAT, isosceles triangle base angle theorem. Also, that leads us to equilateral triangles. Think of equilateral triangles as super isosceles triangles. Why do they call them super isosceles triangles? Because they're isosceles in every direction. We could say every side is equal, therefore every angle must be equal. Remember, we talked about triangles being a very structurally sound shape. That's why they make all sorts of things with triangles. Trusses, ramps, joists. Really, any bicycles have lots of triangles because they're very, very strong shapes. They can't move around like quadrilaterals or pentagons or any polygon of more than three sides. The equilateral triangle symmetry theorem says there are three lines of symmetry for each equilateral triangle. So that line, and that line for this equilateral triangle would all be symmetry lines. And the equilateral triangle angle theorem says that, well, because triangles are so rigid, that if I have an equilateral triangle, that means it must be equiangular. Equiangular means every angle is the same. And we have a corollary that says if I have every angle is the same in a triangle, each angle is 60 degrees. This is unique to triangles. That the equilateral triangle angle theorem. There are other shapes, lots of shapes. We call them regular polygons where every angle is the same. But there, for our next example, would be like a rhombus. Like a rhombus, I can have 4 equal sides without 4 equal angles. This can't happen in triangles, but it can happen in quadrilaterals. It can happen in pentagons, it can happen in hexagons. It cannot happen in triangles. Yeah, it can happen in every other polygon except for triangles. So that is a very unique one. Okay, 6.3, types of quadrilaterals. So the first one is a parallelogram. Parallelogram has two pairs of parallel sides. We draw parallel sides by putting little arrows to denote that they are going the same direction. They're parallel. That is the basic definition for a parallelogram. There might be other things we can realize, and we'll realize those later. Rhombuses. Rhombuses have 4 equal sides. That's the only requirement for a rhombus. A rectangle has 2 pairs of parallel sides and 4 right angles. So I've got parallel sides. It's kind of like a very special case of a parallelogram. A square is the most specific quadrilateral we have. It's 4 right angles and 4 equal sides. Y'all know what a square is. You've known that since well before kindergarten. A kite. A kite is 2 isosceles triangles with a shared base. So that's what the definition y'all gave me. That's pretty good. We could also say it's 2 pairs of adjacent equal length sides. To the left here, we have a conventional convex kite, and here's a non-convex kite. A trapezoid, 1 pair of parallel sides. That's the only requirement. It's quadrilateral, 1 pair of parallel sides. This is very generalized trapezoid, so I've got 1 pair of parallel sides. And then this side and this side really are not parallel, they're not the same length, they're not anything. Then we have a more specific kind of trapezoid, which is a isosceles trapezoid, which has 1 pair of parallel sides and 1 pair of equal sides. So these equal sides are congruent. They're the same length. And then I've got my parallel sides. And then you're asked to draw a quadrilateral hierarchy. Remember, quadrilateral hierarchy, any hierarchy, moves from most specific at the bottom to least specific at the top. Our least specific quadrilateral we call a quadrilateral. Down from there is a kite into trapezoid. From trapezoid, remember everything below what's above is also what is above. So a parallelogram is also trapezoid, and it is also a quadrilateral. So below trapezoid is parallelogram and isosceles trapezoid. And below both of these is a rectangle. So a rectangle is both an isosceles trapezoid, trapezoid, quadrilateral. It's also a parallelogram because it's below parallelogram. And then a rhombus is both a kite and a parallelogram, and a square is both a rhombus and a rectangle. Hope that is clear.